Hello, I'm Jun-Hyuk team from Yonsei University. My research topic is efficient deep learning based lossy image compression via asymmetric autoencoder and pruning. In this paper, we focus on the lossy image compression. The lossy image compression refers to the task of encoding images with as little capacity as possible by discarding some information, while tolerating inevitable quality degradation. The capacity and quality degradation are called rate and distortion respectively, and these two factors have trade-off relation. Generally, rate is measured by BPP and distortion is measured by PSNR. For the conventional lossy compression, JPEG is the most popular one. This figure shows the example of resulting images after the JPEG compression. Recently, deep learning-based methods have been proposed, and they are typically based on convolutional autoencoders. This figure briefly illustrates the whole process of deep learning-based method. First, the convolutional encoder transforms an input image into a latent representation. Then, it is quantized. The quantized latent representation is fed into both convolutional decoder and entropy estimator. The convolutional decoder reconstruct the image and then the loss related to distortion is measured by using MSE or something. And estimated entropy is used for the loss related to rate, because entropy is the lower bound of rate according to the Shannon's information theory. Finally, total loss function is defined by the weighted sum of the two terms. There are some challenges for the deep learning-based methods. First, quantization is non-differentiable, so how to make it enable backpropagation is one of the main issues. Second, accurate modeling of entropy is difficult because we do not have any information of latent representation, so it is also a main research topic. In previous works, these two challenges are well addressed, so they have shown better performance than conventional ones, such as JPEG compression. However, they are still inefficient in terms of storage and computational complexity. This slide shows the contribution. We focus on efficiency of decoders because they are often deployed in front-end devices with limited resources. In this paper, we propose efficient deep learning-based lossy image compression methods in two ways. First, we present an asymmetric convolutional autoencoder. Existing methods are mostly based on symmetric autoencoders, which may not be optimal. Second, by using pruning method, we design lightweight and fast decoders. I'm gonna talk about our proposed method in detail. First, we propose an asymmetric autoencoder. Our rationale is that while the decoder is optimized in consideration of only LD, the encoder considers both LR and LD, which is requiring more parameters for running more roles. In this regard, we designed the convolutional encoder deeper than the convolutional decoder. Specifically, our convolutional encoder consists of one convolutional layer and the combination of a residual block, and a convolution layer is repeated 4 times. And the convolutional decoder consists of only 3 deconvolutional layers. Next, we utilize model pruning method. Generally, pruning can be divided into 2 categories, weight and filter pruning. Weight pruning can make the desired reduction of storage exactly, but it does not guarantee reduction of computational complexity. On the other hand, filter pruning directly leads to the reduction of computational complexity. In this regard, we propose lightweight and fast decoders using weight and filter pruning respectively. For the lightweight decoder, we remove weight whose magnitudes are relatively small. Since the performance of the decoder becomes deteriorated, we retrain the pruned model. These steps are repeated several times. For the fast decoder, we remove filter having relatively large error norms, which is the opposite approach of the conventional method. After removing the filters, we retrain the pruned model. From now on, I'm gonna talk about our experiment. We used 2 types of images, natural and comic ones. This table shows the dataset we used. For natural images, we selected the widely used dataset, and comic images are provided by the Naver Webtoon Corporation. We used BPP and PSNR values for measuring performance, and these are our implementation details. From now on, I'm gonna show our experimental results. First, to show the effectiveness of our asymmetric architecture, we compare the rate distortion performance with the symmetric state-of-the-art method. Here, our asymmetric method achieves the best performance, and the improvement is more noticeable in the comic dataset. In addition, this slide shows that the visual comparison of the decoded images. While JPEG compression generates noticeable artifacts, both the existing and our method reconstruct the original image more clearly. To show the effectiveness of our lightweight decoder, we measure the number of parameters. You can see the results in this table. First, the percentage of the number of pruned parameters range from 50.4% to 69%, which shows that the decoder can be made significantly lightweight. And please note that each pruned model achieves similar or even better performance than the one before pruning. And you can see that the model with smaller lambda values can be pruned more. Smaller value of lambda means that contribution of distortion is smaller, so it allows the decoder to be pruned more. To show the effectiveness of our fast decoder, we additionally measure the number of floating point operations for decoding of an image having this spatial resolution. You can see the result in this table. First, Our model reduced 28.4% and 39% of the parameters and flops, respectively. And our pruning method is more effective than the conventional pruning method, particularly for the commit dataset. To analyze the reason why our filter pruning method is effective, we investigate the characteristic of filters with respect to their L1 norms. These figures show example feature maps in the process of decoding this image. Left part is from the filters with the smallest error norms. You can observe that they are activated in relatively large area and represent overall image structures. On the other hand, the feature map from the filters with the largest error norm are activated in small regions, and they represent only detailed texture. Therefore, you can infer that the filter with larger error norm tend to drop the performance less significantly. To verify the inference, we remove each filter of decoder and then evaluate performance of the resulting decoders. This figure shows the results for both datasets. Overall, when we remove the filter having relatively large error norms, the amount of the PSNR drop is relatively small. And when we prune filters having smaller error norms, the amount of the PSNR drop is larger for the commit dataset than Kodak Photo City. If we consider the filter characteristic mentioned in previous slide, the results make sense because relatively importance of overall image structure is more prominent in comic images than in natural images. This is our conclusion. We proposed efficient deep learning based method based on asymmetric autoencoder and decoder pruning. This is the end of my presentation. Thank you for listening.